In this lesson, we're going to explore specific heat, a really important idea in thermochemistry. Up to this point, we've talked about the kinetic theory of matter and how energy affects particle motion. Today, we'll build on that by looking at how different substances respond differently to the same amount of heat. Why does sand heat up quickly while water warms slowly? Why does metal cool off so fast? All of that connects back to the specific heat capacity. So here is a flashback to the difference between heat and temperature. Remember, as we go through the different states of matter from solid, let me get my laser pointer, solid to liquid to gas, we have more and more thermal energy, we have more and more heat. Heat is the total amount of internal energy, so therefore it is an extensive property. The more you have, the more matter you have, the more heat you're going to have. Whereas temperature is defined as being a measure of the average molecular kinetic energy. And so it works out to be an intensive property. 40 degrees C is going to be 40 degrees C, regardless of how much you have. So here we have two virtual blocks of lead. One weighs 10 grams and the other one weighs 100 grams. Both of them are at the same temperature. Do they both contain the same amount of heat? Hopefully, you said to yourself, well, I know that heat is an extensive property, so therefore the 100-gram block of lead is going to have more heat in it, even though it is at the same temperature. And in fact, the 100-gram block contains 10 times more heat because it has 10 times more mass to it. Here we have two different substances. One is 100 grams of paraffin wax, which is what candles are made out of, and the other one is 100 grams of lead. And we want to know which one is going to require more heat to increase the temperature by 5 degrees C. Now, most people, when I ask them this question, they say the lead because they have more experience with metal objects and temperature changes. Typically, if you think about paraffin wax, you're going to say, oh, well, if you put some heat into it, it's just going to melt. The way you would actually determine which one can absorb more heat is by looking at the specific heat capacity. And the variable abbreviation for that is CP for capacity. It is defined as being the amount of heat, and the symbol we use for that is Q, required to raise 1 gram of a substance by 1 degree C. So we look at the specific heat capacity of paraffin, and it's 2.1 joules per gram degree C. Joules is the metric unit for energy. And we compare that to the specific heat capacity of lead, and that's only 0.126 joules per gram degree C. So it takes roughly 20 times the amount of heat to change the temperature of the candle as it does to change the temperature of the lead block. So now we're going to look at how to calculate how much heat would be required. As I often tell my students, life isn't worth living unless you can do some math. So here we know that our heat capacity for paraffin is 2.1 joules per gram degree C. The equation that you use is given here. It's Q is equal to the mass of the object times its specific heat capacity times temperature change. And so we say, all right, well, I know I have a 100-gram candle, so we have the 100 grams goes in for the mass. We looked up the specific heat capacity for paraffin. It's 2.1 joules per gram degree C, so we substitute that in. And we want to see the temperature change by 5 degrees C, so that's what our delta T is going to be. Delta, or triangle, as a lot of my students say, means change in. So we go ahead and we run that through the calculator, and we get that if this temperature change would require 1050 joules in order to change the temperature of the candle by 5 degrees C. Looking at a different substance, if we had the same amount of heat and we tried to warm 100 grams of water, so same mass, different substance, and we're given the specific heat capacity of liquid water, You have to be sure that you have the right state of matter because the specific heat capacity of ice and gaseous water is only about 2 joules per gram degree C. So liquid water has a higher heat capacity than the other two states of matter. And we want to know what the delta T would be for the water in this case. So we write down our equation again, fill in the pertinent numbers, and solve for delta T. And so if for the same amount of heat and the same mass but a different heat capacity, we're only going to have a temperature change of 2.5 degrees C. So this is going to tell us that for the same amount of heat and mass, delta T is going to decrease as the specific heat of the substance increases. And a comparison I've been using lately, and it's the inspiration for the title slide, is that just imagine heat capacity as being like a bowl. And so you're filling the bowl up, and once the bowl overflows and you start ejecting the heat to the environment, that's when you're going to be able to measure a temperature change. So if you have a low capacity bowl, like this first one, it doesn't take much heat to get it to overflow. If you have a high capacity, you're going to have to add a lot more heat to get in order to get a temperature change. So here's another example. We have 5 grams of copper is being heated from 20 to 80 degrees C. How much energy was used to heat the copper? And I give you the specific heat of copper, which is 0.385 joules per gram degree C. The specific heat of metals is usually less than 1. It's a low number. So we're looking for energy. So we write down our variables. So we're looking for Q, which is our energy. We know it's 5 grams of copper. We have the CP for copper. And our temperature change is always going to be final minus initial. So it started out at 20 and ended up at 80. So that means that our temperature change is 60 degrees C. Plug that into the equation. And you get that it is going to require 116 joules in order to achieve that temperature change. So not very much energy. So a more typical problem would be I'll give you some information and then you have to find the specific heat capacity of something. So the setup is the same. You identify what your variables are, what you have, what you need. So we're looking for specific heat capacity. And so we have, it took 50 joules. Our mass was 3.1 grams. We're looking for CP, and our delta T was 17.9 degrees C. So you plug the numbers in and solve for CP. I've had a colleague who came up with using this triangle method if you're having trouble figuring out how to rearrange the different equations. So just imagine you're covering up CP. That means that CP is going to be equal to Q divided by mass times change in temperature. So then you plug the numbers in and you solve for CP, and you get that, once again, it's less than 1. It is 0.901 joules per gram degree C. And then if you could probably take this further, look up a table of values, you can say, well, 0.901 would be, it sounds like it might be aluminum, I'm not sure, but aluminum is close to that. All right, so one of the ways that you would determine or measure the amount of heat flow between objects, so you can find the specific heat, would be a technique called calorimetry. What it usually entails is you have a known mass of water inside a insulated device. A coffee cup is what we tend to use at the high school level. And then we're just going to put usually a hot object into the water and then measure the temperature change. So we have our experiment is going to be, we're going to heat up some gold, put it into our calorimeter, and measure. Trying to get there's a GIF. There we go. We're going to heat up our gold, put the hot metal into the calorimeter cup, and then measure the temperature change. And so we're recording all of these masses and the initial temperatures and the final temperatures. So let's go on to actually look at the math. So there's all the information. So the first thing you want to do is determine how much heat was absorbed by the water in the calorimeter. This is why you had to weigh that water. And the specific heat of water is very well known because it's how the heat capacities of pretty much everything else is used. It's done in comparison to water. So we say, all right, Q, the water, is equal to the mass of the water times Cp for water times the change in temperature of the water. So now we fill in the numbers. So we add 60 grams of water, Cp is 4.184, and our temperature change was only 1 degree for the water. So now we know how much heat was transferred from the hot gold to the water. So now we're going to solve for the delta T using our Q equals mCp delta T equation. But this time we're going to use all of the gold values. So we had 251 joules worth of heat was added to the water, which means that 251 joules of heat was subtracted from the gold. This is why the 251 is negative when you start talking about using the numbers for the gold. All right, so we have negative 251 joules is equal to 13.5 grams for the gold times the heat capacity, which we just looked up, times delta T. You solve for delta T, and we get that the gold cooled off by a temperature by 143 degrees C. Now, something you have to remember with delta, well, pretty much delta anything, especially when you're talking about thermochemistry, is that it means it's the final state minus the initial state. So we know what our final state was because the temperature stops changing when the gold and the water are at the same temperature. So our final temperature for the gold was 20 degrees C. So negative 143 is equal to 20 degrees C minus our initial temperature, which gives us an initial temperature for that gold block that was put in the calorimeter of 163 degrees C. So this next problem is an example from the worksheet that goes with this particular lesson. One of the things I found that people have the most trouble, or students have the most trouble with when they start doing calorimetry problems, is keeping all of those numbers organized. And so this particular problem, and there's one other one, has a little table that you have to fill in. So I'm going to get my pen going. So it says we have 25 grams of a metal. So our metal has a mass of 25 grams. It is dropped into 200 grams of water. So I'm going to put that 200 there. It says that our metal was initially at 800 degrees Celsius. So I'm going to write 800 in here. And the water was initially at 30 degrees Celsius. So put that in the appropriate column. The final temperature of the system, so both the metal and the water, is 40.22 degrees C. So I'm going to write that. And that means the final temperature of the metal was also 40.22. This is another one of those concepts that's really hard for people to understand. That temperature stops changing when you're doing calorimetry when everything is at the same temperature. So if you're putting hot metal in there, it's going to cool off until the water has warmed up to the same temperature as what it's cooled off to. All right, so now we're ready to do some calculations. I'm going to switch colors. So the Cp for water, like I said, it's very well known, 4.184 0.184. Our temperature change is always going to be final minus initial. So 40.22 minus 30 is 10.22. So now we're going to use the Q is equal to mCp delta T, since we have all the values for water, and we get a value of positive 8,552 joules. Now remember, the water added to, or the heat added to the water is going to be equal to the heat lost by the metal, or the heat subtracted from the metal. So that means that the Q for the metal is going to be negative 8,552. So our delta T is final minus initial. This always bothers people because they're like, well, then I'm going to get a really negative number. That's okay. The metal cooled off by quite a bit. It is negative 759.18 degrees C. So now we're ready to solve for Cp for that metal. So Cp is equal to your Q for the metal divided by the mass of the metal times the delta T for the metal. So Cp is going to be equal to negative 8,552 joules all over the mass of the metal, which was 25, times delta T, negative 8, 5, not 8. Let's erase that. There we go. Times the delta T for the metal, which was negative 759.18. You do the math, and you get that your specific heat capacity is 0.45. When you do these calculations, you will always end up with a positive specific heat capacity. If you end up with a negative value, that means that you lost your negative sign, or maybe you forgot to change it. Down here, where you said, well, the water warmed up, so it's a positive value, whereas the metal cooled off, that should be a negative value. Or you have a negative delta T. So that means the final answer that you would record here would be 0.45 joules per gram degree C. All right, so the Baltimore Shot Tower, this is more of a historical example than anything else. I lived right outside of Baltimore City for quite a number of years, and whenever relatives would come to visit, we would go down to see the Baltimore Shot Tower. The reason why the Baltimore Shot Tower was significant was because it was one of the tallest structures. There were actually like 5 shot towers in the area. This is the only one that is still present. It was one of the tallest structures in the continental U.S. for a number of years. It had to be that tall because of what they were trying to do. What they were making was buckshot. And so the way they made it, so I'm going to turn my laser pointer back on. The way they made it was they would melt a whole bunch of lead metal and then pass it through a metal sieve so that you would end up with droplets of molten metal. And that fall height was enough so that the metal had cooled to the point when it hit the water at the bottom that it wouldn't be deformed. You wanted your buckshot to be nice and round. So in this experiment, we have 100 kilograms of lead, and we're going to heat it up to an initial temperature of 327 degrees C, or that's what it is right before it hits the water. We're going to drop it into 10 kilograms of water. So we reduce the amount of matter by a factor of 10. The initial temperature of the water is 20 degrees C. So we want to figure out what is the final temperature of the water. So we drop it in there, and then we start doing the math. So we're going to be using the Q equals mCp delta T equation. Remember, delta T is final minus initial. The heat lost by the lead is going to be equal to the heat added to the water. So we convert our kilograms into grams, multiply by 1,000. Keep track of all of our signs, multiply everything through, collect like terms, and then solve for final temperature. And we get that the final temperature is 93 degrees C, which is actually pretty amazing, considering how hot the lead started out as. It was right before it hit the water, it was 327 degrees C, and we had 10 times as much lead as we had water, and it only changed by 70 degrees C. Something else that calorimetry can be used for is to determine the amount of heat that is transferred when you have a chemical reaction. So in this case, we have 0.01 moles of sodium chloride in 50 grams of water. So we have 0.01 moles of this. I'm using my mouse again. There we go. So 0.01 moles and 0.01 moles of silver nitrate. So we got a 1-to-1 reaction, so we know that it's going to be 0.01 moles worth of product is formed. In 100 grams of water, temperature of the combined solutions increases by 1.1 degrees C. So there's our delta T. What is the molar heat of reaction in kilojoules per mole? So this part is really important for figuring out how to answer this. It tells you want to take your kilojoules and you want to divide by the moles that are involved in this. So we have 0.01 moles worth of stuff present. Heat is an extensive property, so that means it's going to be limited by how many moles you have present. And so we go ahead and we find the amount of heat needed to warm the water. So Q equals mCp delta T. So we had 150 grams of water total times Cp for water, 4.184 joules per gram degree C, times the 1.1 degrees C increase that we saw. So we had the heat that was added to the water was 690 joules. So that means that this reaction gave off that much heat, because that's the only way the water could have absorbed it. So our heat of reaction, and we use this symbol, we're going to be seeing a great deal of delta H. It's called enthalpy. It just has to do with the heat change or the thermal energy change that goes along with chemical reactions and phase changes. So we're going to take how much heat we had, divide it by how many moles we had. So we end up with negative 69,000 joules per mole. It asked for kilojoules per mole, so we're going to divide by 1,000, and that will give us our final answer. So negative 69 kilojoules per mole. Most of the time, chemical reactions or heat reactions are going to be in terms of kilojoules per mole. So here's another example. So it takes about 5.55 kilojoules of energy to melt one aluminum pop can. And we want to know what its molar heat of fusion is. Fusion is just an old-fashioned term for melting. So we say, all right, well, an aluminum can is about 14 grams, so we're going to find out how many moles that is. So our heat of fusion, it works out to be 10.7 kilojoules per mole. Again, you want to pay attention to the kilojoules and the moles that are involved. You kind of look at the units and use those to your advantage. In 2024, 90,000 cans, aluminum cans, are recycled in the U.S. every minute. It used to be a higher number. People just apparently are not recycling as much anymore, which is a shame. How many kilojoules per second are being used in recycling aluminum cans? So we go ahead and we say, all right, well, it's 90,000 cans every 60 seconds, every minute. We know that we have that many moles per can, and then that it is 10.7 kilojoules per mole. So this is kind of like using dimensional analysis, factor label method, to determine how many kilojoules per second are involved. And it works out to be 8.33 or 8,330 kilojoules per second. Do some more conversions, and that works out to be about the same as burning 1,990 food calories per second. Now, athletic people, very active people, they can get away with having a diet that's over 2,000 calories per day. Can you imagine trying to burn off that much energy in every second instead of in a whole day? And I kind of looked this up as an aside. How much energy is required in creating an aluminum can as compared to just melting one that already exists. It takes it's more than 500 times more energy is required to start out from the aluminum ore and get all the way to producing a aluminum can. So we really need to start recycling more. My mouse does not want to advance. This slide reminds us that during a phase change, temperature remains constant. All of the heat energy goes into breaking or forming intermolecular interactions, not to speeding up the particles, which would increase the temperature. Because of that, the specific heat equation doesn't apply. So instead, we're going to have to use enthalpies of fusion and vaporization. So this is where that delta H comes in. So here we have our heating curve of water. So we're going to just kind of focus in on the plateaus where we have it melting. That would be the heat of fusion, and it's the amount of heat needed to convert a solid into its liquid phase. Like I said, fusion is just an old-fashioned term for melting. And then in order to go from a liquid to a vapor, it's going to be the heat of vaporization. That would be, liquid to a vapor, gaseous phase. All right, so that's about all I can think of to say about specific heat. So just to wrap it up, heat is a total amount of internal energy, which means that it is an extensive property. So the more you have, the more heat more matter you have, the more heat you're going to have. Temperature is a measure of the average kinetic energy of particles in a substance. It is an intensive property. Specific heat is the energy that is needed to change the temperature per gram of a substance. They used to do things in terms of just heat capacity, which is probably where that CP came from. But then you'd have to take into account what the mass was to begin with when they measured it, because of that whole extensive property thing. So now they use specific heat so that you know it is on a per gram basis. The greater the specific heat capacity, the smaller the temperature change will be for the same amount of heat. We saw that with our comparison between the temperature change for 100 grams of a paraffin candle versus 100 grams of water. In calorimetry, it's an experimental technique that we use in order to measure the amount of heat transferred between different objects. The heat that's lost from one substance, so it's going to have that negative Q, is going to be equal to the heat gained by another substance. It's conserved, you can't lose it or create it from nothing. And remember, delta T is always going to be final minus initial. And then phase changes, as we saw at the very end there, use delta H because there is no temperature change. which is why we can't use the Q equals mCp delta T. And I think that's it. So that's it for specific heat. Next time we'll be talking about enthalpy, heat, and chemical change. Thanks for listening.